This video is sponsored by Squarespace, the all-in-one website building tool. Planets go around the sun in elliptical orbits, right? But Mercury's orbit is a little weird. Turns out that it keeps precessing like this. Why does it happen? Well, for a long time we thought it had something to do with the gravitational influence of the other planets. But careful observations show that that accounts for about 92% of the precession. And just like how my mom used to ask me a question when I used to hand over my report card, we're going to ask over here, what about the remaining 8%? Well, the answer that I always got was space-time curvature. But my problem with this is that doesn't help me understand anything. This particular visualization doesn't help me understand how it makes Mercury's orbit precess. And I feel this word space-time curvature is just thrown around these days casually as if it actually explains anything. Hey, why does gravity bend light? Oh, that's actually very easy. You see, mass just curves space-time and light just follows that space-time curvature, yeah. Okay, but then why people age differently, like what we saw in Interstellar? See, there is space and there is time. So the space and time is curved. So it's that curvature that makes us age differently. Just so easy. Okay, right? At least can you tell me why can't we ever escape from a black hole? Oh, that's really a good one. Okay, see, inside a black hole there is space, yes, and there is time. That space-time is curved. That curvature. Where are you going? It's curvature. That's the one. So by the end of this video, not only are we going to visualize and build a model to understand how spatial curvature actually makes the Mercury's orbit precess, we'll also be able to understand why in 1911 paper, Einstein made a huge blunder in predicting the deflection of the starlight by our sun, and how in 1915 he actually corrected it. It'll all make intuitive sense. So if you're ready for this, let's begin. So where do we start? Well, Lewis Epstein, the author of the book Relativity Visualized, says, Mahesh, let's say we shoot a beam of light, a photon of light from point A to point B somewhere in space. I'm like, okay. Now he says, Mahesh, I'm going to shock you. All right. What if we repeat the same experiment, but this time we put a planet in between and drill a hole so that light can pass through it? He now asks, does the light take now the same time as before to go from A to B? More time or less time? Well, as I'm thinking, Epstein says, I'm just going to spoil the suspense for you. Turns out light will actually take more time to go from A to B when I keep the planet over here. And this is indeed shocking. I am shocked. The reason I'm shocked now is because if this was not light, if we were dealing with, say, apples over here, if we threw apples, apple would actually go faster through the planet because the planet would actually accelerate it due to gravity, right? It would go faster. But light is now going slower because of the planet. So that is indeed shocking. Epstein, why does this happen? And Epstein says, Mahesh, we need to go back to our space-time diagram. And we've talked a lot about this space-time diagram before, but just as a quick refresher, because I don't want you to go back and watch the whole video again, just as a quick refresher, in this space-time diagram, everything always travels at the speed of light. If something is at rest, that means it's traveling at that full speed through time. So it will be ticking, its time will be ticking at the maximum rate. But if it starts moving through space, that means it'll tilt some of its velocity, it'll tilt like this, and so some of its velocity is through space, and so its velocity through time will be less. Its clock is now ticking slower compared to this one's. And of course, if you completely move through space, then all your velocity will be moving through space. You will not be moving through time at all. That means now you're moving through space at the speed of light. This is basically light. And now to visualize this in our ordinary spatial and temporal terms, we turn it into a cylinder. When we do that, the cylinder becomes the space, the curvature of the cylinder becomes our proper time. And now the things that are at rest will just keep ticking at a maximum rate. So just keep circling over here. Things that are moving will circle slightly slower because it's also moving forward through space. And things that are moving at maximum speed through space, well, they cannot move through time at all, so they don't circle the cylinder at all. That's basically your light. And now what happens if there's a planet close by? Well, for that, we again consider two objects at rest, and then we brought our planet, and then we know that clocks over here are ticking slower compared to clocks over here. Therefore, this must be a bigger radius. In other words, this turns into a cone. That's the effect of the planet. Okay, end of refresher. Now, if you feel good to go, well, let's proceed. But if not, I've talked about this in great detail in our previous video, so do feel free to check that out. But anyways, let's now go back to Epstein's problem. Epstein says, Mahesh, let's draw our space-time diagram for these two cases. Well, for the first case, it's quite straightforward. It's just going to be a cylinder. And since we know that light is traveling at the speed of light through space, it's not going to circle over here at all. It's just going to go like this. Okay, but now comes the big question. What does this space-time diagram look like for the second case? Well, here's how I like to think about it. If I go far away from this planet, imagine point A and point B are very far away from the planet, the effects of the planet is negligible, which means the space-time diagram should look similar to what we have over here, cylinders. But what happens if I go closer and closer to the planet? I know that the clocks will start ticking slower and slower and slower. That means its radius should become bigger and bigger and bigger. Until when? Well, clocks will start ticking slower and slower and slower until you reach the center of the planet, right? I mean, think about it. Even if you go inside the planet, you're still lower in the gravitational field. So as you go lower and lower, clocks will tick slower and slower. The radius will become bigger and bigger and bigger until you reach the center. Once you pass the center, now you're sort of like going up on the other side, right? And now, just like over here, it'll be symmetrical. So it'll be now, the radius will start becoming smaller and smaller and smaller. So if you put it all together, you're going to get a space-time diagram that looks like this. Now, Epstein says, even though this is complicated, a good way to get an intuition is to approximate this. We can kind of approximate this by saying that there are two cones over here. Remember, our goal is to get an intuition. So even though it's not absolutely correct, it's fine. Okay, so now if I were to draw the path of light, what will it look like over here? Well, it'll be the same like over here. It's going to be straight, but this time, because the cylinder flares out into a cone, look, the path of the light gets bent. And therefore, this path now is slightly longer than this path. And that makes sense, right? Now it's not straight line anymore. It is bending, so it has to travel more path. If I were to draw little arrow marks, each arrow mark showing the distance light travels in 1 second, that's the same. Light is traveling at the same speed. But if you count the number of arrows, you will now see there's one extra arrow over here. This is the reason why light will take more time to go from here to here, not because it has slowed down or anything, but because there is now more space. Somehow, look, there is more space created. That's why light ends up taking more time to go from here to here. So the effect of having a planet is that it creates more space between 2 points. Now I'm like, oh, wait a second, hold on, Epstein. Are you saying that when I bring a planet over here, these 2 points A and B kind of like move farther apart somehow? And Epstein says, no, that can't be true. Remember, far away, the planet has negligible effect. So the 2 points stay put. And yet somehow, without making the 2 points go farther away, it is increasing the distance between the 2 points. That's the effect of the planet. And I say, how does that make any sense? How can you increase the distance between 2 points without moving the 2 points farther away? That doesn't make sense. And Epstein says, of course, Mahesh, it doesn't make sense to your Newtonian brain, but that is what it is. That's the effect of planets on space. And I'm like, okay, but how do I visualize this? Is there a way to do that? And Epstein says, yes. Because our brains cannot wrap this concept around in our heads, here's a way to visualize it. Let's consider another diagram. This is not a space-time diagram. This is just a space diagram. Instead of showing 3D space, I'm just showing 2D space. So this is space diagram, not space-time. I already have a space-time over here. Okay. Let's say that the planet is somewhere at the center over here. Now we know far away, the points, these far away points will not be affected. And yet somehow I need to increase the distance between this point and say this point. In other words, I have to put more paper somehow between these 2 points without stretching them away. How do I make sure there's more paper in between now? Well, one way to visualize that is to put a bump over there. If I put a bump, well, now you can clearly see there's more paper over here from all directions. There is more paper now. I have increased the distance between the 2 points without moving them farther away. This is the reason why we show a warp in space to represent that there is more space created by massive objects. Now, wait a second, I say Epstein, wait a second, why did you show the bump to be upwards? Like the bump should be actually downwards like this, right? That's how the bump should be. And Epstein says, Mahesh, remember, this is just a visualization. This is not what's really happening. At the end of the day, what matters is you're going to put some wrinkles over there just to increase the distance between the 2 points without stretching them. That's just a way to visualize it. That's it. So Epstein says you can build it any ways you want. You can build it downwards. You can build it upwards. You can put wrinkles. You can build anything you want. Just like how you can build any website you want using Squarespace, the sponsor of this video. I wanted to build FloatHeadPhysics.com, but for that I need a domain. Where do I get that? Well, I just went to Squarespace.com, clicked on this button which said Get Domain, bought my domain, and boom, FloatHeadPhysics.com became live. Next, I wanted to build a website. Now, since we can build any kind of website, I wanted to make a portfolio, but I have no website creation experience. Well, guess what? Squarespace comes with hyper customizable templates. So I just clicked on portfolio, picked the one that I really liked, and then I changed the pictures and I edited some of the fonts and moved things around. And after a few hours of just clicking buttons, my website, FloatHeadPhysics.com, was fully ready. Is that incredible? However, unlike me, if you're a professional, then you can build your own templates. Decide how your home page should look like, how all the other pages should look like, how they all connected, fonts, colors, everything, and then edit it exactly as you would want. But that's not all. They have incredible analytics to help you understand how your website is doing. They also have incredible support, which will unblock you whenever you get stuck somewhere, which happens to me a lot. And so yes, you can use Squarespace to build any kind of websites you want. So if you want to start creating digital presence for yourself, which I think everyone should for free, then you can go to squarespace.com/floatheadphysics and use the promo code FloatHeadPhysics to get a 10% off on your first purchase. The link is also in the description below. All right, back to spatial curvature. Now it's time to reap the fruits of all the hard work that we've done over here, because we can build a model of this and we can actually see how it affects light. To do the model, all I need is a paper and a cone. Again, we can approximate this as a cone on top of it. So let's do that. Feel free to do this along with me, okay? So all we need is a piece of paper and a circle, which we're gonna cut into a cone. So to make it a cone, we put a slit over here and then just fold it and boom, we get a cone. And we will tape it, but I'm using this tape because it should be removable, okay? We will see why it needs to be removable. But anyways, once we do that, and I keep it on top of it, boom, there we go. This is the model of the curved space. I now have more space from here to here because of that bump that we have shown over here. Now let's see how this affects the path of light. So to do that, I'm just gonna draw a straight line. And now to make sure to draw that straight line on this, I'm gonna flatten this a little bit and draw a little bit, extend that line a little bit. Okay, there we go. And now to continue drawing that line on the cone, I'm just going to remove that tape. Okay, now I'm gonna draw again a straight line. Light always travels in a straight line. All right, and now I'm gonna put it back. I'm gonna turn it back into a cone. And here's the big moment, folks. Ready for this? When you turn it back into a cone, what do you see? Look at what we get. Look at what we get. We get the light bending. There you go. Light is bending over there, even though we drew it straight. Now I know a part of my brain is saying, well, Mahesh, it's obvious. Like if you draw a straight line and you bend it, you turn it into a cone, it'll bend. But it's one thing to see it. It's one thing to see animations of it, read about it. But it's a whole different thing to actually do it while remembering that you are trying to understand Einstein's theory of general relativity. I challenge you to do this without bringing a smile. It's impossible. When you do it, there will be a smile that comes on your face when you actually see that light bending. This is incredible. Please do it. Don't like, don't subscribe, don't share. Just do this. Just do this, please. Okay. So now I'm going to put it back. All right. So I drew always straight lines. I'm going to put it back where it was to where it was. And then I'm going to do the same thing to extend and see where that light goes. Same thing. Always straight. I always drew straight lines. And look at that. Look at that. Spatial curvature affects light. It bends light. And you can actually, you can actually draw the original direction of light. You can do that. And then you can actually see that there is an angle between the original direction and the direction in which it has gone. So for example, if the sun was over here somewhere and you can imagine there was a distant starlight, then you can clearly see that there is some angle of deflection. And because of that, when you see it from here, that star appears to be somewhere over here. Isn't that incredible? Isn't that beautiful? But wait, let's calm down a little bit because I have a major doubt. See, earlier we said that light bends because of the equivalence principle. Just to again refresh our memories, remember how Newton said that there is a gravitational field downwards, but Einstein said there is no such thing as gravitational field. Instead, the whole thing is accelerating upwards. And we call this the equivalence principle. We said that these are two indistinguishable from each other, right? And so now if this is initially at rest, and let's say I shoot a beam of light, then that light will go straight, but this will accelerate up. And so as a result, we will see that, that beam of light can actually hit the floor in a greatly exaggerated way. But from the equivalence principle, the same thing should happen over here, which means if I shoot a beam of light, it should also hit the floor. So we should see the same thing, and therefore we will see light bending. And so earlier we used the equivalence principle and we said it's due to the equivalence principle light will bend down. But now we are saying that light is bending due to spatial curvature. Well, which one is it? Epstein says both. Now we're starting to get a full picture of general relativity. In earlier videos, we talked about the equivalence principle, which actually brought out the ideas of time dilation, which is the same thing as saying time curvature. And from that, we get light bending. But in this video, we saw that spatial curvature can also bend light, which means if you want to actually find out the deflection, the correct deflection of this starlight, we need to add both these effects. And so the actual deflection of light will be more than what you see in this model because we have to also consider the time curvature. So because we have space-time curvature, finally, that's why light deflection will be more. We have to add both the deflections. And now we can understand Einstein's 1911 blunder. In that paper, he had only considered time curvature and the equivalence principle. He had yet to develop the ideas of spatial curvature. That's why he predicted the light that should be bending will be less than what we know today is to be true. And if you think about it, the same predictions would happen in Newtonian physics. Because remember, even in Newtonian physics, you can say light bends because everything falls down regardless of its mass or whatever that is. And therefore, you will get the same result because in equivalence principle, you always get the same result. And so in 1911 paper, Einstein predicted that the light should bend the same amount as Newtonian physics predicts. But Einstein got lucky because in order to test this out, you need a solar eclipse. I mean, how else will you see stars when there is sun over there, right? And then there was World War, and then there were climate conditions and so much. Because of that, experiments could not happen until 1919. But by then, Einstein realized that he should also consider the spatial curvature. And in 1915 paper, he correctly considered the spatial curvature as well and predicted that the deflection must be more. It just so happens to be for sun, and when you're close to sun, it just happens to be twice as much. And therefore, the deflection of the starlight would be twice as much as what Newton predicts. And we tested it out and the experiment actually agreed with these results. But that now brings us to my final doubt. If the deflection of light is twice as much as what Newton predicted because its behavior is affected by both spatial and time curvature, shouldn't the behavior of everything be affected by spatial and time curvature? And so shouldn't everything behave very differently than what Newton predicts? Why does the world look Newtonian then? This is where Epstein reminds us that, hey, remember that most objects around us, including you and me, are mostly traveling through time. We're hardly traveling through space compared to speed of light, remember? So most of our speed is through time, and therefore we are mostly affected by time curvature. And since time curvature, the effect of time curvature is almost indistinguishable from the effects of Newtonian gravity, we see Newtonian gravity everywhere. So the spatial curvature hardly affects us, but its effect is there, okay? And that's what brings us to the weird precession of Mercury's orbit. So if you draw the Mercury's orbit over here, again, we can model it. This elliptical orbit, well, that's because of the time curvature, okay? But there is some spatial curvature. Now let's account for that. To put a spatial bump, just like what we did before, I will just put a slit over here. We don't need a cone. We just put a slit over here and we'll put one piece of paper on top, one side of it on top of the other, just to show the bump. And now just see what happens when I do that. Here we go. When we do that, look at that. What do we see? This is greatly exaggerated, of course. But what do you see? There is a spatial curvature now. You can see the bump. But the effect of the spatial curvature is that the orbit does not close in on itself. And because the orbit does not close in on itself, you can see the far point of that ellipse is no longer over here. So it's not over here. It has moved. And if I continue to do this, if I just add more images, you can see it keeps moving. This is precession. So the precession is explained by the spatial curvature. And when we did the math, it actually accounted for that 8 missing percent that we found earlier. So it all worked out. So we now have seen all the 3 tests of general relativity: the Pound-Rebecca experiment of gravitational time dilation, which we saw last time in our previous video, the orbits, the precession of the Mercury, and the deflection of light, which was twice as much as what Newton predicted. We've done it, and hopefully that gives us now more confidence in general relativity. So did the video live up to the promise of making things way more intuitive than just saying space-time curvature? Now the actual space-time curvature, we have modeled it all, hopefully makes more sense. But now the question could be, where do we go from here? Well, the obvious next question would be, how does this all change when we go close to a black hole? We now have all the tools necessary to rigorously talk about black holes as general relativistic entities, and that's what we'll be doing in our next video. So if you want to stay notified for that, do subscribe to the channel. But if not, it's completely fine. No hard feelings. But at least do the model. Please do the model. It's going to make your day. Trust me. See you. Bye.